that would be an option, because yeah, or you share your screen and then we discuss something. But maybe the easiest way is you send me something, you try something and you send it to me on Slack where you get stuck, and then we try to solve the problem. Okay, because that will be important, that we slowly get to the exercises, because they are so important. Okay, so I will share my screen now. Okay. So last lecture, we have derived the dispersion relationship for Rossby waves. Essentially, using this equation here. But ignoring this term. Oops. Ignoring this term. Because then everything, the geostrophic vorticity can be expressed in terms of the geostrophic stream function. And that is the equation that we have been used, that we have linearized, and then derived the dispersion relationship of Rossby waves. Those waves that propagate in positive zonal direction, where the energy propagates in positive zonal direction. And the waves themselves, they can propagate to the west and to the east, depending on their wavelength. But we noted that if we take just this part of the equation, this conservation of absolute vorticity, this is what it is, then this set of equation is closed as it is. We don't need anything. There's no interaction with any other equation, with the thermodynamic equation or so. This was a very useful thing. So we could easily solve this equation. And we found that the dispersion relationship actually was real. There was no imaginary part appearing. That means that if we initially prescribe small amplitude perturbation, this small amplitude perturbation will not grow and not decay, will just propagate and does disperse according to its dispersion relationship. But there won't be energy gain or decay for such a wave. So so far we are not able to explain how waves can gain energy, but we have already some idea, because when we looked at the orographic forced Rossby waves, we have taken into account this term here, this divergence term. But there it was easily possible to kind of prescribe this term, the effect of this term on the vorticity. But in general, if we don't have a mountain that has an easy shape, and this divergence term can be related to any vertical velocity that is not just forced by mountains, but that can be generated just in the atmosphere. The atmosphere has vertical velocity. The vertical velocity is not zero. Then this term has to be dealt with. And that is a complication to our treatment. But that makes the system also more interesting. So that is what we want to do today. We want to look at this equation here, which is again the vorticity equation, just in the same way. We use the stream function, which is, in this case, we consider we are in the pressure coordinate system. So the stream function, geostrophic stream function, is defined by geopotential divided by F naught. So we assume that we are at a We can fix some kind of latitude, but then we have to consider the variation of Coriolis parameter in the close vicinity of this latitude. But on the right-hand side of this equation, we want to allow this divergence term to be present now. This is now the big difference. If this term is 0, again, we can linearize this equation and solve it, no problem. But once this term is present, and we cannot find a simple parameterization of it, we have the problem that we have now not anymore just one variable, psi, the stream function, but we have two variables, omega and psi. So we have to try to close this system. How can we do this? Now, of course, we have inserted here already the continuity equation. That doesn't help because the continuity equation just replaces the ageostrophic wind, which is not expressed by the stream function, and the omega field. So the continuity equation, okay, cannot close this. We can just use it to express this right-hand side, either in terms of horizontal divergence or in terms of the omega by dp. But in order to close this equation, we have to use a different equation. And this equation that we use is the thermodynamic equation, which is shown in this equation here. Now, it doesn't seem the thermodynamic equation, because here should be the temperature. Right, let's go back to the thermodynamic equation, which we have derived for the pressure coordinate system. This is the thermodynamic equation. For the purpose of this lecture, so this was already the quasi-geostrophic formulation where we have kind of split off already the vertical derivative of temperature. So that part is already contained here. For the purpose of this lecture, we will set as many times the diabatic heating term to 0. That makes the treatment more simple. In reality, the diabatic heating term will be there in the real world, but we have to reduce in order to make analytical treatment. We have to reduce as much as possible the complexity of the system. So this is the equation that we want to use. So how comes that there is this d stream function by dp in terms of temperature? Does someone have an idea? How can we replace temperature by the vertical derivative of the stream function or geopotential? It's quite clear. Now we just have to use the hydrostatic equation, where we have inserted, where is it? This equation here. This is the hydrostatic equation in pressure coordinates. So d phi by dp, which is d geopotential, you know this, by dp. We replace the density by the perfect gas law, and then we get the temperature here. So this allows us to express the temperature in terms of derivative of our geopotential or stream function. That's what we do. So we insert in our thermodynamic equation the hydrostatic equation, and we get here, we insert this here. We set this term to 0. And we get back to the system of equations that we have just looked at. Which is this equation here. Just multiplied by this. We multiply this by the stability then that occurs here, the stability parameter, and divide it by F0. And we get to this equation. And this is now a closed system of very complex system of partial differential equations. We have two coupled partial differential equations. And the major complication is that whereas before we only had to take into account derivatives in the horizontal direction, now we also have to take into account derivatives in the vertical direction. So instead of having a two-dimensional problem, or we could even simplify it to one-dimensional problem if we assume the wave is not propagating in meridional direction. Here we have a three-dimensional problem because we have to take into account the vertical structure of our stream function. But in principle, this set of two equations is closed in the sense that we have two variables now, psi and omega, and we have two equations. So the momentum equation expressed here is in terms of just its vorticity, and the thermodynamic equation, they provide us again in this geostrophic, quasi-geostrophic formulation, a closed set of equations. This makes the waves that we are looking at more complicated, obviously, because as we will derive in this lecture, this will allow our waves to become unstable for the first time. So we may be able to describe the growth of the waves. We will see that we are really talking about always the possibility that waves are just growing. They can also decay, but there will be always a growing part. Now, this, in principle, one can solve this set of equation, linearizing it, and then try to solve in the three-dimensional frame. That can be done, but it's extremely complicated. So what we are doing is some kind of, we use a brute force again. And this model that is used to simplify this and to solve this equation is called ED model of pyroclinic instability. So what ED has proposed is, okay, let's try to keep the system as simple as possible. And instead of using, trying to solve it in a three-dimensional frame, we just discretize the vertical direction in a very, very crude way. So I will now open another document. Give me a second. Here it is, okay. So the setting that we want to use is this following. We discretize our system in the vertical direction. That makes the treatment then almost as simple as for the barotropic Rossby waves, because we don't have to consider any more propagation in this vertical direction. The partial differential equation becomes more simple. And what we use is some kind of a staggered grid. So we define omega. So first of all, we have kind of 4 levels in principle. So the top level here is at 0 pressure. And at 0 pressure, we have this simplification, of course, that omega, which is the derivative of pressure. If the pressure is perfectly 0 always, then omega is also always 0. And then we have level 2, level 1, level 2. Again, omega is always defined at this at the even pressure levels, whereas we use the staggering that the stream function, and this will turn out to be useful. The stream function is defined at the odd levels. So at level 1, at level 3. That is a useful setting. And so also at level 4, this would be, let's say, 1000 hectopascal, which is close to the surface level. At this level, we assume for our treatment that omega at this level is equal to 0. This is an approximation, because whereas the vertical velocity, if we don't have any orography, the vertical velocity has to be 0 at the ground, the physical vertical velocity. But the pressure vertical velocity is not exactly 0, but is only approximately 0. At the surface, the omega can be different from 0, because there can be, in the individual, this is the total derivative of the pressure, and that can be different from 0 at the surface, but not the vertical velocity. Anyway, for the treatment here, we assume that this is small enough to be set to 0. And then we define our pressure difference. That would be a delta P that we consider, for example, between level 2 and level 4, the same between level 1 and 3 and level 0 and 2. This pressure difference is 500 hectopascal. This is just, we say, by our definition, this is our discretization. So we have the level 0, 250, 500, 750, and 1000 hectopascal. And we use a staggering that allows us to easily express vertical derivatives, for example, using variables that are defined at the other levels. So this is the setting, and that removes the vertical derivative because we have discretized this already. So this simplifies our system a lot. It makes it less exact, but much more easier to treat. So we go back to our, now you see this lecture again, right? Okay. So this is what we do. Now we want to discretize these terms. Now, first look at the stream function equation. Remember, we apply at level 1 and level 3. So we have to evaluate the right-hand side here at those two levels. But there's the derivative, so we can express the derivative, as you well know already from your numerical methods course. We can evaluate this approximately by the vertical derivative. So omega at level 2 minus omega at level 0 divided by the pressure difference. And the same with the derivative at level 3. Now we can make use of the fact that omega 0 and omega 4 are 0. So the only variable that remains is omega 2. The velocity, the vertical velocity at this mid-level is the only vertical velocity that remains here. So if we write down our equation for the stream function for both levels, level 1 and level 3, so remember 250 hectopascal and 750 hectopascal, one relatively low level and one quite high level, close to the tropopause. Then we can write this equation in this way. Now for the thermodynamic equation, we apply at the mid-level, not at the level 1 and level 3, but at the mid-level 2. In order to do that, we have again to express this vertical derivative as a discretized vertical derivative. So stream function at level 3 minus stream function at level 1 divided by the delta P, which is 500 hectopascal. And so we can express our thermodynamic equation in this way after multiplying by this delta P. So instead of having this delta P here, we multiply it over here. And we get this equation here. The good thing is, again, we know psi 3 and psi 1 because they are defined at their proper levels, at level 1 and level 3. So that is not a problem. Also, omega 2 is a variable that is defined at that level 2, which is fine. The problem is here that we have here the velocity advection at level 2. Now, velocities are related to horizontal derivatives of our stream function at that level. So this is what we have said here. So our velocities are, so u2 would be defined by minus d psi by dy, and v2 would be defined by d psi by dx. But we don't have the stream function at the level 2. That means we have to evaluate the stream function and velocities. Therefore, at level 2, we have to use average values between level 1 and level 3 because we know stream function only at those levels. So we express the velocities and therefore stream functions at this level. We express them as the average stream function between level 1 and level 3. With that, in principle, if we have this, in principle, then our new set of equations, it's still nonlinear, as you can see. It's a nonlinear set of equations, but it's in principle closed because the variables that we have are psi 1, psi 3, and omega 2. And we have 3 equations. The vorticity equation at level 1, vorticity equation at level 3, and the thermodynamic equation at level 2. So in principle, the set of equations is closed. So we could try to solve this numerically, for example, in this simplified version. Simpler to solve because it's not 3-dimensional anymore. We have removed the vertical dimension by discretizing it. But we want to linearize it in order to understand stability and the characteristic equation for this problem. So we want to simplify it further by linearizing it, as we have done already in the last lecture. So we linearize this equation by assuming, again, that our stream function can be expressed as a mean part plus a perturbation. And the mean part has to fulfill the original equation, and the mean part does fulfill the original equation. Because the Laplacian of this will be vanishing, so that is fulfilling it. But as you can see, we use something interesting here, different from what we have done for our barotropic Rossby waves, because we allow the velocities at level, the mean velocity at level 1 and at level 3 to be different. They can be the same, and we will make use of this property later in the discussion, but we allow them, in principle, they can be different. What does this mean? So that is a vertical shear of the mean wind. If you remember the thermal wind equation that you have shown, what is this? What is the vertical shear of the zonal wind proportional to? It's the meridional shear of temperature, right? That is what you have shown. When the wind changes in the vertical direction, that has to be balanced by a horizontal change in temperature. So what comes into play by allowing this here is the effect to have a meridional temperature gradient. The temperature difference between equator and pole, if you want, comes into play here. In our case, just the part that we can see in our channel of this meridional temperature change. But this is just the way it enters our equation is simply by allowing for the mean flow to be different in both levels. And for the perturbation stream function, we make a simplification. We say, okay, in general, this could be a function of x, y, and t. But for simplicity, we say, okay, let it be just a function of x and t. So our waves only propagate in zonal direction. And for the vertical velocity field, we assume that there's no mean vertical velocity. All the vertical velocity is related to perturbation vertical velocities. This is intuitive, because we cannot have that there's a mean rising or sinking of the motion in our channel. That is not reasonable. So it's reasonable to assume that the vertical velocity is just, so the average of the vertical velocity is zero. The mean vertical velocity is zero. There has to be, what comes up has to come down. Otherwise, we will have a loss of mass in our levels. So this is the setting for our mean flow and for our perturbations, with the extension that we allow the mean flow to have a shear between our two levels. And now we can using this, we can linearize our equation. So again, as before, we ignore higher order terms in the perturbations. Now this is a little bit more problematic potentially, because if, as we find later out is the case, if our perturbations can grow in time, then these solutions may not be, the linear form of the solutions may not be valid for a long time. So we have to take this into account. This may be only valid for a few time steps, or for, let's say, in terms of for a few days or something like this, because then if we find that our perturbations can grow, then at some point this will not be valid anymore. But no, this is just for the purpose of doing the stability analysis of the equations. Initially, we can define our amplitude to be small enough such that the higher order terms in perturbations are zero. So we only consider the first order terms in this equation. And you can easily work out that the perturbation vorticity equations and thermodynamic equations now look like this. This is again a complete set of equations. So after the linearization, we can immediately work out the solution for this, because we will insert later on again sine and cosine waves for our perturbation quantities, and that will solve the system. So we have our three perturbation quantities: psi1, psi3, and omega 2. And we have three equations. So this will solve this linear set of partial differential equations. Homogeneous, because there's no term that is not related to any, proportional to any of the variables. But before we insert perturbation quantities, we will modify the system a little bit. So it is useful for the later treatment to express, instead of using U1 and U3, we can express them as, we can use the mean flow as the mean flow between the two layers, and the thermal wind, the change of the wind between the two layers. So we can simply reverse these equations to replace U1 and U3 in these equations, and you can work out that this gives us for U1, UM plus UT, because if we add the two, then the U3 goes out. But if we take the difference between the two, then the U1 goes out. And so these are the equations that we get. And for the thermodynamic equation, we make a further substitution. It's just a substitution. We define the mean stream function between the two levels that we have, where we define the stream function, level 1 plus level 3 divided by 2. And we define the thermal stream function, that is the change of the stream function with height, the perturbation stream function between the two levels. And then we can again express the second equation alternatively with these new variables in this form here. This is just a substitution. It's not really necessary, but it's useful for the interpretation. Doing this now, we can, first of all, we can eliminate omega 2 between these two equations by just adding them up. If we add these two equations up, then the right-hand side here vanishes. And we get an equation. But we can also derive another form for the thermodynamic. No, this is the result for this equation here, right? This is the stream function equation by adding these two up. Then this term vanishes, and we get this equation here. However, we can combine them in a different way in order to eliminate omega 2, and we get to this equation here, which is due to the thermodynamic equation. So now we have simply transformed our set of 3 equations into a set of 2 equations by eliminating omega 2. We managed to derive 2 equations for the mean stream function perturbation psi m and the stream function change, perturbation change with height, psi t, because omega has been eliminated here. So this gives us now a closed set of equations. One equation is purely related to the stream function. The other is also related to the thermodynamic equation. They both, in this linearized form, constitute a closed set of equations. We could have also, as I said, it wasn't necessary. We could have simply inserted already perturbations for psi 1, psi 3, and omega into this equation, and the final result would have been identical. But it's more kind of intuitive to do it this way. So we have now these 2 sets of interacting equations. Now we insert our Fourier components. This is, we have a linear set, a homogeneous linear partial differential equation. This should be solved by sine and cosine functions again, where we assume that our waves that we try as solutions here, they can only propagate in the zonal direction, because the meridional direction, we have set our waves we have defined our waves not to propagate into a meridional direction. We could have done this, and that wouldn't have made any big changes to the calculation. But in order to keep it as simple as possible, we just assume that they are propagating in zonal direction. The vertical direction is not there anymore because we have removed that. And when doing this, so we insert the mean stream function and the mean perturbation stream function between the 2 levels and the thermal perturbation stream function. We insert this here in these 2 equations. And we know, again, how to deal with these derivatives, because d square by dx square will give us k square minus k square, and so on. Time derivative will give us minus ik c, and so on. So it's very straightforward, right, to do this. This leads us, after dividing by this exponential, to these two coupled equations for our amplitude factors A and B. Now remember, this can be written as a matrix. This would be the matrix applied to A and B. So it would be this matrix applied to the vector A and B is equal to 0. This can only have non-trivial solutions. So A and B is equal 0 are always solutions, which is not what we are looking for, 0 solutions. But this can only have non-trivial solutions if the determinant of this matrix is equal to 0. So the determinant, again, as you remember, is this times this minus this times this, which is written in this expression here. So this is now a quadratic equation for C, for our phase velocity in x direction C, which gives us the dispersion relationship. Easy to solve because we can, this is just a quadratic equation. We know how to solve a quadratic equation analytically. You may call it PQ formula or whatever. It's very easy to do. So the solution is this one here. There is something interesting happening here because we have plus or minus this square root of this delta, whereby delta is defined in this way. Now, this is very different from our barotropic Rossby waves, because now, if delta becomes negative, then our phase velocity has an imaginary part. If our phase velocity has an imaginary part, our solutions are not purely oscillating anymore, because we get here imaginary part times imaginary, so that would be either growing or decaying solutions. The thing is that we have a pair, plus and minus. So there will always be one solution that is decaying, but there will also be always in this pair one solution that is growing. So we have now this possibility that if delta becomes negative, that our Rossby waves that we have found here, for which we have found the dispersion relationship, they may not only propagate, but while they are propagating, they may grow. And they grow because of this instability that is included here. And we want to discuss this instability. So that will happen if this delta is negative. And this can be nicely discussed because there are two terms that can compete with each other. But first, it is useful to look at the special case, which remember, the special case of the thermal wind equal to 0 removes the instability. Because if the thermal wind, the change of the wind with height, which is proportional to the meridional temperature gradient, if that is 0, then the delta here is positive. And if delta is positive, we cannot have any, taking the square root of this, will not give us any imaginary part in the phase velocity. So that is an intuitive result. If the thermal wind is zero, if there's no temperature gradient where our waves can gain energy from, then our waves will be stable. And if you evaluate this, so it's easy to take the square root of this because everything is already squared. Nevertheless, we find two solutions because there's the plus and the minus. If you do this, you will find that these two solutions look like this. One, the C1, is just exactly like the Rossby wave, because if the wind doesn't share, this is just the U that we have used in the last lecture, minus beta over k square. This is exactly the phase velocity for Rossby waves that just propagate in zonal direction. So that is exactly the same result. We have recovered the result from our last lecture for purely barotropic Rossby waves, where we don't have the effect of vertical motion in principle. But the second solution here is still similar and is, as it should be, real, but we get an additional term. So it's not anymore just beta divided by k square, but it's beta divided by k square plus something that is proportional to the stability of our atmosphere. So this additional term comes into play because we have this possibility that all our waves will have the possibility to include vertical motion. And this was completely excluded when we looked at the Rossby waves in the last lecture. We didn't include the possibility of vertical motion. But our waves here, they have this possibility to have vertical motion. And that kind of reduces their phase speed. That reduces the retrograde tendency. So this is always, of course, always positive. So that will reduce this tendency for the waves to retrograde for the second mode here. And if you did one exercise in the last lecture for the ocean Rossby waves, then there was also something for the ocean Rossby waves with a free surface. There was also an additional term that reduced the speed of those waves, which was F naught divided by G times the height. And that was also related to the fact that in those waves, we had the possibility of vertical motion because we have a free surface. So that is kind of an analogy for that case. So before going further, I'd suggest we make a 10 minutes break. So I see you again at around, let's say, noon at this point. Okay. So I stop sharing. Hi. Can you hear me?
Yes.
Okay. So let's go back to this lecture. So we have treated now the special case where there's no instability because the thermal wind, the mean thermal wind was 0. But now we want to discuss the case when there can be instability. Now, the one way forward to do it, it's a quite complicated problem, but one way forward to do it is to look at the limit case where we are on the edge of instability, on the edge of this delta becoming positive or negative. So that this limit we can investigate by setting delta to 0. Setting delta to 0 gives us this equilibrium between these two terms. So we get this this equation here, which we can resolve, and there's a reason for doing this. For k, the wave number to the power of 4 divided by 4 lambda to the power of 4. It turns out that lambda has just the same magnitude, the same dimension as the wave number, so 1/meter. And therefore, this is a dimensionless quantity. And you can work out, okay, that then this is equal to 1/2 square root of this expression here, where we have another dimensionless quantity appearing here. So this 2 lambda square UTB is another dimensionless quantity. So we can draw this limit of stability. We can draw as one against the other, the wave number against the, if we want to, the baroclinicity, this wind shear with height. And if you do this, you get to this curve here, where with the two-dimensional quantities, this is now expressed in terms of k square, so the square root, divided by 2 lambda square on the y-axis, and 2 lambda square divided by ut beta on the x-axis. And these are the two square roots that I have drawn here. In this area here is the unstable region. In the region outside is the stable region. So waves become, so one thing we can see is that the beta effect is always stabilizing our system, because without the beta effect, this would be always, delta would be always negative, and we would always have an imaginary part. But the beta effect is actually stabilizing our system, so make it possible that there are stable solutions that don't grow in time. So, and this, as we can see from these two roots, these stable solutions can exist for small wave numbers, so for long wave, and for very short waves. Now we want to do one thing. Imagine we want to figure out if we are, let's say we start in this stable range. So our thermal wind is such that we are in this range here. And now we increase our thermal wind. So we move a line closer to this unstable region here. And there's a point where we can just touch. So the line is not very straight. Where we can just touch this unstable region. So we increase instability until we touch this curve here. Formally, this is equivalent to differentiating equation, this equation here with respect to du by dt. So turning on the whole thing on the other side and calculating du by dk is equal to 0 and setting it to 0. But we don't have to do this. We can just imagine we increase the thermal wind until we reach the instability. And that is the point. That is actually 1. And so this point is where the waves for the first time become unstable given a thermal wind. This is the wave number that with the minimum thermal wind becomes unstable. And then if we move further, we increase the thermal wind further, we get a large unstable domain. But this is the first time the wave number becomes unstable if we increase our thermal wind coming from the stable region. And so this wave number is just determined by this value 2 lambda over ut beta equal to 1. So the wave number that we can find is k square is equal to square root of 2 times lambda square. So this wave number that becomes first unstable if we increase our thermal wind is related to the stability of the atmosphere. So it turns out that this wave number, if you work out the wavelength that is related to this wave number, we get to something that is 4,000 kilometers, which is actually the typical wavelengths for perturbations that we see in our, if we look at the large scale atmospheric flow, Rossby waves, then this is a typical wavelengths that we will find. So we may imagine that that our atmosphere is always on this limit of, in the mean, on this limit of instability, and sometimes we get in the unstable range, and then this is the first wave that grows in that case. We have seen already an example for such a growing wave, which was our very first picture that we looked at when we were starting the lecture course. If we go way back to the very beginning, we looked at this very situation here, where we had just a meridional temperature gradient and no horizontal temperature changes. And that would be our initial situation. And then you have seen that this meridional temperature gradient is related to this vertical change of wind. So this is a typical situation that we have just treated. We are obeying our thermal wind relation, which is the one that you have proven to be true. In your case, you have shown it already for the pressure coordinate system. And then, as I mentioned, we wait 5 days. You put in it some tiny initial perturbations. You have to put in some, but they can be as small as possible, just some noise initially. Maybe magnitude can be 10 to the minus 20, whatever, very small numbers of perturbations. And then after 5 days, we get these waves in our system. So now remember, this was the x-axis and this was the y-axis. So interestingly, the wavelength of this channel is just 4,000 kilometers. So in this example, of this numerical example of a growing Rossby wave, that is indeed exactly 4,000 kilometers, that wavelengths. So there's one one low pressure and one rich in this case. And as we discussed already, what these systems do is they transport the warm air from the tropical regions to the extratropical regions, and the cold air from the northern latitudes to the southern latitudes. And by doing this, they generate perturbation energy, generation energy that could be both kinetic and also potential energy from this reservoir of mean energy. The energetics that is related to this, we will discuss in a few lectures later. But I can tell you already what is happening is how this energy, this instability that we have found, how this energy is actually released in these systems, is that this warm air, this warm light air is actually rising, and the cold air is sinking. So in principle, this system, they lower their center of mass and therefore release kinetic energy. This is what all extratropical systems do. They manage to use this mechanism by lowering the center of mass. They are able to release this kinetic energy that is in the present and in the stream function flow. And so this is exactly the mechanisms that make these systems grow, which is this pyroclinic instability, which is present always if we have the situation with a meridianal temperature gradient, which is always balanced by this vertical wind shear. So that is the case when our waves can grow. We just have to need this meridional. So that means on average, we will always have the possibility for these Rossby waves. They don't just propagate, keeping their magnitude constant. They amplify while they propagate because of this pyroclinic instability. And then sometimes they may not be growing because the beta effect is able to overcome the effect of the pyroclinic instability. But on average, they will always grow. Then, of course, there are damping mechanisms. So there will be what makes them not always grow is also the effect that we have frictional dissipation, of course, in the real world, which we have completely ignored. A further mechanism that we have ignored here, and that may be very important in Rossby waves, in particular small scale propagating cyclones and particularly cyclones, is the fact that we have completely ignored the heating term in the thermodynamic equation in order for us to be able to treat this system as much as possible. So we have seen that in order to get pyroclinic instability, we don't need any heating in extratropical cyclones. But we know that this is happening. We know that in extratropical cyclones, you have seen Trieste now already for some time. So you know that in these extratropical cyclones that are affecting also the weather here, we have a lot of rainfall. That means that there's a lot of diabatic heating also contributing to the energetics. But this is just a secondary effect. This is not the first order effect of cyclones growing, is this pyroclinic instability that can be large if the thermal wind is and the temperature gradients are very large. Then we get this these waves growing, and that is the case, and particularly in what we call the storm track regions. So in the the Atlantic and in the Pacific, there are regions where we have a very strong meridional temperature gradient, particularly on the coast, on the east coast of the United States, and then also on the same side of the coast of Asia, where the temperature gradients are very pronounced. Now, in terms of exercises, I don't want you to do this exercise. It's just in addition, what can happen if you include some kind of frictional dissipation term. But please don't do this exercise. This is not necessary. I just want to tell you that in the next lecture on Wednesday, we will completely change now. Not completely, but to some extent, change subject and go away from these extratropical regions where we found this very interesting instabilities. And we will look at waves in the tropical regions. Similar type of waves, Rossby waves, but then in tropical regions, we will see that also gravity waves are very important for our treatment. Tropical regions are in some ways easier to consider, but in some ways also much more complicated to consider. I remember in last year's lecture, we discussed this a little bit. Pyroclinic instability is very interesting and is very well understood for extratropical cyclones. But for example, if you go to the tropics, of course, you are wondering, so what is happening to tropical cyclones? For tropical cyclones, pyroclinic instability, at least at the initial state, is not supposed to play an important role. So tropical cyclones do not gain out of this temperature gradient mainly, but they gain energy out of completely different mechanisms. So a hurricane will gain energy out of the surface energy fluxes that make hurricanes grow. So the energy growth that we have just discussed is purely relevant for extratropical cyclones, not for tropical cyclones. We will not discuss, at least during this current lecture, the tropical cyclones. They're a separate subject that I won't cover in this lecture, but also very interesting, much more complicated. So the extratropical cyclones are very well understood, as I said, but tropical cyclones, there is still a lot of research going on as to what is exactly happening during their energy growth. But the waves that we will discuss in the next lecture, they are also very well understood. But the treatment that we would do again is even much more simplified than the one that we have done for the extratropical waves. But this is what we have to do in order to treat our systems analytically. We have to try to simplify the system as much as possible. Also sometimes risking to oversimplify in the sense that, yes, we can gain some information out of our analytical treatment, but then we also get some things that we have simply to impose in order to get back solutions that are somehow reasonable. So for example, for the equatorial wave theory that we will discuss on Wednesday, we will assume again that we have the shallow water equations, barotropic shallow water equations, in order to derive the simplest way of equatorial wave theory. And this is completely, in principle, completely wrong, because the tropical regions are regions where our velocities strongly change with height. So in the tropical regions, usually when we have at the surface convergence, we have divergence at the upper levels. But we will treat our system in a way that either we derive a solution just for the surface, or what is more the case, we will derive our solutions just for the upper levels and understand wave propagations at that level. But we will discuss this in more details in the next lecture. Okay, so with this, see you on Wednesday. And I encourage you, if you have anything to discuss, maybe you can submit something on Slack, and then we can discuss this in the beginning of the next lecture regarding the homework. Okay? Okay. Bye then.
Thank you.
Bye. Thank you.
Bye.